All right, so the other application of derivatives that tends to be, again, not emphasized very heavily on the AP exam, but is pretty common and it's important, useful application is optimization. This is it's I would say similar in difficulty to related rates in that the problem is usually the setup is the trickiest part. The actual calculus portion, not that complicated. Your goal in this problem is to identify the objective function. That is the thing you are trying to maximize. And you want to get that in terms of one variable. That's like super key. Anything, that's your goal in optimization. You want to find what is the function that I'm trying to optimize, or what is the thing I'm trying to optimize for. Make it a function, put it in terms of one variable, and then we're going to use our, finding our techniques for finding absolute min or max or relative mins or maxes in order to answer that question. So it's easier if you see it as an example, but of what we're going to try to do. Because ultimately, at the end of the day, is we're trying to create a function, and we're ultimately just trying to find what is the maximum or the minimum of that value of that function. That's what optimization is all about. So let's take a look at this first problem here. A rectangular box with an open top is to be made of a square piece of cardboard. Okay, a squared piece of cardboard by cutting one square from each of the four corners. So you're going to cut a square here in each of the four corners. And then what you're going to do is once you cut them up, the sides can fold up, right? Like these will fold along here. And here, and here, and here. So you're going to cut out these squares, and then you'll fold along the dotted lines into an open type box, right? So you have to do a little bit of visualization here. Okay, if the piece of cardboard, it measures 12 by 12. So we know that this thing is 12 inches by 12 inches. Determine the size of the squares to cut out to create a box with the maximum volume. Okay? So my goal is to construct. So what am I trying to maximize? The volume. I need to create a volume of this box here. Okay? And let's just say, for example, like, the base is going to be a square. Let's call that X, X, and we'll call this the height Y. So like this will ultimately a box that is X times Y. Right? This is the base here, and when you fold it up, Y here is like the height of that thing, Y. Okay? Now, or X squared Y. Now, again, this is in terms of two variables, right? You should add as many variables as you need in order to get the volume expression, but this is in terms of two variables, X and Y. Okay, so I've gotten the X squared Y here as the volume. So now it's like I need to get rid of the variables X or Y. I need to get rid of one of them because I need to have this in terms of a single variable. Okay, so what do I know? What do I know about this 12 that will relate? Well, I know that this is Y and this is X. So I know that like the sum, this entire length has to add to 12. Okay, so that means 2y plus x has to equal 12. And I can solve for x and then plug that into here to get rid of the other variables, right? So instead of x, I'm going to replace it with 12 minus 2y squared times y. And that's going to be my expression for my volume. Hopefully that part makes sense to you, okay? So that's that. And our goal then is to find the y that makes v the biggest. Now, technically speaking, you're doing an absolute maximum here. A lot of times people still focus on, more relative maximums, but I'm technically trying to find the absolute maximums, which means I need the bounds for what y can be. We know y can be between, say, 0 and 12. Or actually, 6 is the biggest I can make y. Why can't I make y bigger than 6? Because if I make the square, like y is like how much I'm cutting out of the square. If I make it half of that thing, I'm not going to be left with any volume. And, the smallest I can cut the y is y. I can't make it like negative. So it's definitely within this range here. So to find the absolute maximum, so how do we find absolute maximum? We do the candidates test, right? So we're going to take the derivative and set it equal to 0. So let's do the derivative of this guy. I'm going to do product rule between this and this. Okay, so this has the derivative of this guy, as I have to do power rule, times the derivative of the inside, which is -2. Okay, and then times y. So that's the derivative of this function times y. And then this function times the derivative of this guy, which is just 1. Now, notice, unlike related rates or implicit differentiation, I'm taking the derivative with respect to y, because I'm picking the y that's going to maximize it. So it's not like I need to throw in any like dy dt's or dy dx's, because I'm not taking the derivative with respect to x, I'm just taking the derivative with respect to y, because I'm choosing the y that's going to make this as big as possible. So if you look at this, you can factor out a 12 minus 2y. So when you have something like this, and you want to set it equal to 0, you can factor out a 12 minus 2y here. And what am I left with is 2 times -2 times y, which is -4y. And then I'm just left with a 12 minus 2y over here, because 12 minus 2y times 12 minus 2y would give me 12 minus 2y squared. And I do that because that will give me some useful that will allow me to solve this. So minus 4y, this would be 12 minus 6y equals 0. Now, if I solve this, that means if it's equal to 0, it's already factored here. So all I did was combine the like terms there. It's already factored here, so either this is 0 or this is 0. Here you're going to get y is equal to 2. Here you're going to get y is equal to 6. Now, 6 is already your bounds, and 2. So then, remember our candidates test, we're going to pick 0. Oh, sorry, we'll put y. 0, and 6, and then 2 as our critical points. And then we're going to find the volume. And the volume is equal to 12 minus 2y squared times y. Now, if I plug in 0 to here, I'm just going to get 0, because this 0, I'll make it 0. If I plug in 6, this will be 0, so I'll get 0. So 0 and 6 actually were minimums, because my volume can't be smaller than 0. If I plug in 2, I can get 12 minus 2y, 12 minus 2 times 2 is 4, squared times 2. That's going to give me 8 squared times 2, 64 times 2 are 128. So that means the size of the squares, which is a y by y square, that's the square I'm cutting out, is 2. So it's a 2 by 2 square, 2 inches by 2 inch square. And that will give us the maximum volume of 128 cubic inches. Okay, so that's the idea. Let's do another example here. Let me move this downward. Let me give a little space here. You have 500 feet of fencing to enclose a rectangular field next to a straight river. So we have a river here. This is a river. This is a classic problem you do for optimization. You have 500 feet of fencing. Find the dimensions of the field that will maximize the enclosed area. So I don't need fencing along the river here. So then I'm going to create fencing that looks kind of like this. And what do I want to maximize is the area. Okay, so let's say that this side is x, this side is y, and this side is x. It's a rectangular field. And I don't need fencing over here. So the area is going to be x times y. This is what I want to maximize. Okay, but I got to get it in terms of one variable. And a lot of times that comes from a constraint. There's something in here that relates x and y that makes it, because otherwise just make it as big as possible, then that would make it big. But the constraint is the fencing. I have 500 feet of fencing. That means the perimeter has to add up to 500. Okay, so it's 2x plus y has to equal 500. And then what you can do is solve for y or x, but I'll solve for y because it's easier, and then plug that into here to get area in terms of a single variable. Right? So and if I distribute, it's 500x minus 2x squared. So then I want to think about what is the biggest and smallest x can be, right? X, I have to use at least 0, right? It could be 0. And the most x could be is like if I made y 0. The biggest I could do fate is just like 250, then 250 back, right? Like that would be really bad, but like 250 is the most I can make in this dimension, because then I would run out. I wouldn't be able to construct the rectangle. And that's it with rectangle with 0, by the way. So we have some bounds here. So let's find the absolute maximum. So we're going to take the derivative, which is 500 minus 4x. And we're going to set it equal to 0. This is finding our critical points. So our x is 500 divided by 4, which is 125. And then we're going to look at what makes our area maximum, right? Is it the endpoints 0 and 250, or is it 125? Now, 0 and 250 are going to make these 0, actually. If you plug in 0 into here, you'll get 0. If you plug in 250 into here, this part will be 0. You can check on your calculator. You plug that in, you're going to get 0. What about 125? It's going to be 125 times 500 minus 2 times 125, which is 250. And that's going to be 125 times 250, and that's going to be 31,250. Either way, this is the maximum. This is the largest value of the endpoints or of the critical points. So then we would say, what is the dimensions of the field? It's going to be the x is 125 feet, and the y, you just look at this expression to find our y. It's going to be 500 minus 2 times 125, which is 250 feet. So the maximum area is going to be 125 feet by a 250-foot area. Okay. So again, the goal is to find that objective function, get it in terms of one variable, and then we run the method to find absolute maximum. Okay, let's do one last example here. So we have a cylindrical can estimated to hold 1 liter of liquid. Find the dimensions that will minimize the amount of material needed to manufacture the can. Note, neglect the material of the top and the bottom. So we're just talking about the side parts here. Okay, so a trickier one is to include the tops and the bottom. So we have a cylindrical can. So we're just going to talk about the material on the side here. Now, what are we talking about? What do we want to minimize? Minimize the amount of material. If I make a can from this, I'm minimizing the area because the can is hollow. It's not the volume I'm trying to minimize. It's the actual, like, the sides of the can. Right? It's like the area of it. So it's really surface area. And let's assign some variables. Let's say we have the radius of the can and we have the height of the can. And we know that the surface area is going to be, this is just a formula to know, but I think of it as if you unroll it, it's a sheet of paper, because it's like a thin sheet. You unroll it, the area is literally the circumference times the height. Okay, and that would make a rectangular sheet. If you were to unroll this can to flatten it out, the length of it would be the circumference of the circle times the height. So again, I can't do this in terms of 2 variables. I got to make it in terms of 1 variable, so I have to relate r and h in some way that I can get rid of that in this equation, because this equation has to only be in 1 variable to find the maximum. Well, we know the constraint is that it can hold 1 liter of liquid. This is a volume. This is how much it can hold, it can fill inside the can. So the volume of a can is the area of the circular base times the height. Right? So that's pi, and that has to equal 1. Okay, and so what we can do is we can solve for h, say. You get 1 over pi r squared, and then plug that into here to get it in terms of 1 variable. Okay. So then the r cancels, and I get, and the pi cancels, so I get 2 over r is the area. Okay. Hopefully that makes sense. Yep. So then I'm going to take the derivative. So now it's in terms of 1 variable here. So we're going to take the derivative and set it equal to, let me see if I did this right. So surface area is 2 pi r h. I just want to double check. I feel like I made a mistake somewhere in the math, but let me double check. Nope. Okay. I don't think you can neglect the top and the bottom. I think this is a mistake in the notes. So I'm going to say we're going to ignore the top and the bottom. Yeah, this problem, I think there's a typo in this problem. I'll fix it in the notes, basically. But we can't neglect the top and the bottom because you're going to get something that's not really solvable. You're going to get negative 2 over r squared when you take the derivative. And you can't set that equal to 0, or r is going to be infinite. So we can't neglect that part here. So let me just add in the area of the top and the bottom of the can. Those are areas of circles. Each area is pi r squared. So then we're going to have plus 2 pi r squared. So this is going to work better. So then the area is going to be 2 pi r times 1 over pi r squared. That was my mistake on the problem, and that's because what's going to happen is you wouldn't get an optimal. The answer would be like you should make a super flat, skinny one, but that's not going to work. So the pi here cancels, the r here cancels, so you get the area is equal to 2 over r plus 2 pi r squared. Right, that's the area. So now I have it in terms of one variable, right? So then I'm going to take the derivative. Derivative of this is negative 2 over r squared. You can make it r to the negative 1 and do power rule if you want. And the derivative of that is just going to be 2 pi. Derivative of r squared is 2r. Right, so you get negative 2 over r squared plus 4 pi r. And again, this has to equal 0. And you can move this over. 4 pi r equals 2 over r squared. You can move then you can multiply the r. You get r cubed is equal to 2, or r cubed is 2 over 4 pi, which is 1 over 2 pi, or the r is going to have to equal the cube root of 1 over 2 pi. Okay, so that's the radius. Now, what are some other bounds? R can actually go from 0 to infinity, okay, technically, right? Like r, like those are some bounds on here. So when we're trying to find which one area is going to maximize or minimize, we're going to plug in different values of r. We'll do r, 0, the cube root of 1 over 2 pi. And if you plug in 0 into, well, it's not really 0, but if you look at it, like, yeah, if you go towards 0, this is going to be infinite, right? Because this guy's going to explode, right? So it's going to be infinite. And because I'm trying to find the minimum amount, minimize, so I want the smallest value. That's infinity. If you plug that in here, you're going to get some number. You know, it's going to be 2 over cube root of 1 over 2 pi plus 2 pi times r squared, which would be the cube root of 1 over 2 pi squared. Kind of a very ugly expression, to be honest. And then if r were infinite, right, like that's the other bounds, then this thing is going to go to infinity. This will go to 0, but as r goes to infinity, kind of like our limits, like this is going to explode to infinity. So this is definitely our minimum. Right, so the dimensions are, like, I don't know the exact amount, but it's definitely smaller than the two end bounds, which are going to be infinite. So that's the cube root of 2 pi, and then to find the height, it'd be 1 over pi r squared, which would be 1 over pi times the cube root of 1 over 2 pi. Now, typically speaking, on the AP exam, you don't have to simplify very much as long as you get something grossly correct like that. But if you wanted to simplify, you certainly could. Oh, we put a square there. Because I just used, to find the height, I just used, yeah, this expression that we had for the height. And that would be the dimensions of the can that would minimize the amount of material, right? Because from our bounds and from this, we got the minimum. So we got the minimum there. This is the smallest number from our candidates test. So there's more practice problems. These take a lot to set up. But it's the same idea. The tricky part is always the setup to get it in terms of one variable, right? You want to find your objective function, try to get it in terms of one variable, so then you can use your candidates test to find the absolute min or the absolute max. So in these problems, we're going to be looking at optimization. Optimization is a pretty common topic in calculus, and like related rates, the biggest part is to make sure you set it up. And then we're going to use our techniques to maximize or minimize a given function using the first derivative test or second derivative test. So that's the general idea. So here's find the maximum product of two numbers that have a sum of 100. My first is a setup is to just say like, okay, the product is equal to two numbers. We'll say x times y. And then they have a sum of 100. So that means like of my two numbers, I know that they have to add up to 100. Now, in calculus that we've learned so far, the way to maximize a function is I need to put it into one variable. I can't do these derivatives with more than one variable. Like I don't know how to maximize or minimize that. That is for multivariable calculus, which is later in your career if you continue down math. So in this case, to make this a function, this is really a function, p of x. Okay, or p of x and y in this case. To make this a single function of x, I can solve for y. Y is 100 minus x. And so this is going to be x times 100 minus x. Or I can distribute and get 100x minus x squared. Okay, so now this is good. Now I have a function I can maximize. And I'm going to attempt to figure out what the maximum value is. Now, to do that, I'm going to take the derivative. So I'm going to take the derivative of this it's going to be 100 minus 2x equals 0. This is how I find my critical numbers, right? That's how I find the maximum of a graph of a function. First I find the critical numbers. This would be x is equal to 50, as you can see. Okay, now we have to determine, is this our minimum or maximum? Well, I can use a second derivative test to tell me that this is equal to -2. This is less than 0. This is a maximum because it's concave down. So I mean, x equals 50 is my answer. That also means my other number is y is also equal to 50 because they add up to 100, and so that would give me the maximum product. Oh, they actually wanted the maximum product, and the p would be 2500 in this case. 50 times 50. Okay. Here's find the maximum sum of two positive numbers. So I want to maximize the sum whose product is equal to 500. And so by the same thing, I want to say this is y is equal to 500 over x. I need to get this in terms of one variable. So this is x plus 500 over x, right? And so s prime, the first derivative, is going to be 1. And then 500 x to the -1, the derivative of that would be -500 x to the -2, which is equal to -500 over x squared. So this is going to be 1 minus 500 over x squared is equal to 0. So I rearrange this. That gives me x squared is equal to 500. So x is equal to plus or minus the square root of 500. But because this is telling us two positive numbers, I only want the positive number. So this is going to be x is equal to, I can take out 100, so it's 10 root 5. Okay. Now I want to know if this is a positive, is this a maximum or a minimum here? You can think of it intuitively as to say, like, well, it would probably be a maximum, because like the minimum would be like if this is like 0, then the sum would be like 500. Well, I don't know actually. So let's actually compute this. So I could do second derivative test. So the second derivative test, looking at it from this form, it's going to be -500 times -2 x to the -3, and that's equal to 1000. The positive, because the negatives cancels over x cubed. This is greater than 0, so this is going to be a minimum. Okay. So, so what are the? So if this is a minimum, maximum sum of two products. This is a minimum. Yeah. So general this shape. I think it's not going to have a maximum, because if I plotted this curve, when it's really small, it's going to go like down here, and then it's going to go like, oh, this function. So it's x, it's a line plus this. I'm trying to just get an idea of what kind of curve I'm looking at. But there doesn't appear to be a maximum because of the way the first derivative. Are there any other critical numbers to deal with? 0, but 0 is not a critical number, even though the derivative would be undefined there. We need two positive numbers whose product. I can't include 0, because 0 times anything is not going to be 500. Yeah, I think this makes sense. I don't know if this makes sense to you, but if x were a tiny number, like x was like 0.001, then y would have to be like 500, 1000, and then this sum would be like 500,000 and 0.001, right? So to maximize this actually doesn't really make sense. There's no maximum value, because as long as x goes smaller and smaller and smaller, y is going to get bigger and bigger and bigger, and the sum's going to go to infinity. So there is no maximum. It can be any value. And so that's one reason why we sometimes have to check the first or second derivative, because you might have said like, oh, I have one critical number, and so that should be my answer, but that's actually a minimum. Okay, so I don't know if it's a typo in the problem or if it's a kind of a trick question. Find the maximal area of a right triangle with hypotenuse of length 5. So I have a right triangle here, length 5, and we're going to say this is x and y. So the area is equal to 1/2 x times y, right? That's what I don't know. But again, I need to relate x and y so I can put this in terms of one variable, and I can use the Pythagorean theorem. that this is true. So that means y, if I solve for it, has to be the square root of 25 minus x squared. And so then I'm going to plug that into here. The area is 1/2 x square root of 25 minus x squared. Okay, so to maximize, I need to find the critical numbers when the derivative is equal to 0. Bring out the 1/2, and I'm going to do product rule between these two functions. This is going to be x times the derivative of this. This I write as 25 minus x squared to the 1/2, so I can use my power and chain rule correctly. That's 1/2 25 minus x squared. 1/2 minus 1 is negative 1/2 times, but the inside's not x, so times the derivative of the inside, which would be negative 2x, plus I brought this 1/2 out, plus the derivative of x, which is just 1, times 25 minus x squared to the 1/2, just the radical one there. Okay, and then I want to factor out, so this 1/2 and this 2 cancels. I want to factor out the largest term, the smallest term of 25 minus x squared. That's negative 1/2, because this is the smaller exponent. And so if I pull out here, I'm left with negative x squared plus, and then I think about what times this would give me this, just a 25 minus x squared to the 1 power, because 1 times negative 1/2 would make this positive 1/2. So this is 1/2 25 minus x squared to the negative 1/2 times 25 minus 2x squared, because I got an x squared and another x squared subtracting. That has to equal 0. This is going to go in the denominator, so for this to equal 0, all that matters is this part. So 25 minus 2x squared is going to equal 0, and so 25 over 2 is equal to x squared, and so x is equal to plus or minus, we'll just make it plus, we use positive sides, is positive 25 over 2, root 25 over 2, and that's 5 over root 2, which is 5 root 2 over 2. Okay, so that's what I got for that. Now I have to determine whether or not this is a maximum or minimum. Physically speaking, this is going to be a maximum, because the minimum area, like if I made x really like 0, the area would be 0. So you could think intuitively that this is going to be the area. But let's just confirm that it is by looking at the first derivative. And I'm going to do the first derivative because the second derivative is kind of annoying, so I don't really want to do that. Okay, so this term's always positive down here, because when you take the square root, it's always positive. This up here is going to be, if I'm bigger than 5 over root 2 and I square it, if this term is larger, it's going to be negative, and if it's smaller than root 5 over 2, it's going to be positive. So it's going to go from positive to negative. That makes it a maximum. So that's that. The y value would equal root 25 minus this squared, which would be 25 over 2. So that's also root 25 over 2. So x and y are equal, which should make sense. It's kind of symmetric. So the area is going to be equal to 1/2 root 25 over 2 times root 25 over 2. And that's 25 over 2, 25 over 4. Okay. Number 4. I have a standard soda can is roughly cylindrical and holds 335 cubic centimeters of liquid. What dimension should the cylinder be to minimize the material needed to produce the can? Oh, okay. So the volume is 355 cubic centimeters. The material needed is the surface area. And the surface area is made up of 3 pieces. It's made up of 2 circles and the lateral area. So each circle has an area pi r squared, and there's 2 of them. So it's 2 pi r squared plus the side here. If you unroll the cylinder into a flat sheet, it will look like a rectangle. Rectangle with height h, and length would be 2 pi r, the circumference of the circle. Okay, so this is the surface area, and this is what I want to minimize, right? Because the less material I need to make the cylinder, the cheaper it would be. So this is, but the problem is I have 2 variables here, and I want to optimize. I need to put it in terms of 1 variable. So I look at the volume here. The volume is pi r squared h. And now I get to choose which variable I want to solve for. And I guess I'm going to solve for h because it's like kind of the easier one to replace. So h is going to be equal to 355 over pi r squared. So I'm going to put that into here. So this is equal to 2 pi r squared plus 355 over pi r squared times 2 pi r. So this is going to be 2 pi r squared plus 2 times 355. That's like 710 over r. Okay, so we're going to call this the area. So a prime to max. So this is what I want to maximize. That I want to minimize. I want to minimize the area. Well, if I take the derivative of this, I'm going to get 4 pi r minus 710 over r squared, because this is r to the negative 1, just doing power rule. At this point, hopefully you've practiced that enough that we can just do the derivatives a little bit faster. Equals 0. I can multiply through by r squared, and so I'm going to get 4 pi r cubed minus 710 is equal to 0, because 0 times r squared is 0. And then I can solve for r, so I'm going to say r cubed is equal to 710 over 4 pi. And so r would then equal to the cube root of 710 over 4 pi. Okay. Now, if I were to do a second derivative test, you'll find that this is a minimum. Yeah, the minimum area. Because as you make it thinner, to hold the same amount of volume, it will have to be like super, super, super long. So you could do a second derivative test to confirm that. But that is the dimension of that. And then to find h, I'm going to do 355 divided by pi times cube root of 710 over 4 pi squared. Whatever number that happens to be. You can use your calculator to do the rest of that. Okay. Woman throws a stick into a lake for her dog to fetch. The stick is 20 feet down the shoreline. Okay, so I need to draw a picture here. And 15 feet. So there's a stick right here. We'll say this is the water. And this is... okay, so... the dog's here. Okay. And 15 feet into the water. So this distance here is 15 feet. And this distance here is 20 feet. Okay? And here's the dog. The dog may jump directly into the water and swim, or run along the shore to get closer to the stick before swimming. The dog runs about 22 feet per second and swims about 1.5 feet per second. So in general, you might think this is sort of like, okay, should the dog run straight? Well, because he runs at different speeds, we're going to try to optimize the point. So the key part of optimization too is to like put it in terms of one variable that I need to optimize. Okay. And I'm going to do another picture of a stick so it doesn't look like an X here. So here's the stick that's in the water. Now I'm going to I'm going to say this is x equals 0. And I'm going to say x is some point, okay, here, that the dog is going to run to and hit the water, and then it's going to run from the water into here to get to this, and swim from here to get to this point. Okay. Yeah, sorry. It should be how far along the shore. Sorry, let me pick this. This shouldn't be. It's all part of this is all part of the question here. Oh. How far along the shore should the dog run to minimize the time it takes to get the stick? So we're gonna. This is what we're trying to do. Is we're trying to create an equation that minimizes the time it takes to get this stick. So I need to from this picture. I need to find an equation for time. Okay, the time it would take. Well, let's see. 20 feet down the shoreline and 15 feet into the water from there. Oh, actually, the dog is like more like over here. I see. This is a little bit simpler. Is along the shoreline like this. Okay. So we're gonna pick the point at which the dog is going to run along the shoreline and then cut into the water. Because at some point it has to cut in the water. Does it go all the way? Does it come out a little bit and then start going? Kind of depends, right? Because ideally a straight line is sort of the best. Okay, so we'll call x the point at which the dog enters the water. So we need an equation for time for this. Well, in general, the velocity that you're running at is distance over time. That's a basic concept that we'll have to use for this problem, that the speed that I'm running at is the distance divided by the time. So the time is equal to the distance divided by the velocity. So first I'm going to say the time he runs down the shore, well, he runs a distance x. So the t1, the time to run along the shore, runs a distance x, which I don't know what x is. X is the variable that I'm going to use. But his velocity is 22 here. Okay. Now here we have to figure out, okay, now he's going to swim this distance here. I need to know this length. To do that, I can figure out, and I want to do it in terms of x. And I know this length here is 20 minus x, and this is 15. So by Pythagorean theorem, this is 20 minus x squared plus 15, right? Squared. So the second time we're going to do is we're going to have this is going to be the distance over the time. It's this distance divided by velocity. So that's 20 minus x quantity squared plus 15 squared. All of that divided by its velocity, which is 1.5. And so the total time, what I want to optimize for, is the sum of these two times, x over 22 plus this time here. I'm going to try to simplify this part a little bit. Actually, no, we'll just leave it like that. I think the derivative, because what you want to think about is what derivative am I going to use, or what derivative rules I'm going to use, and we'll just use this. The derivative is easier that way than having to bother to expand. Okay, so t prime equals 0. That's how I find my critical number here, right? Oh, sorry, this is, actually this is, yeah. So t prime, this is derivative with respect to x. So this is, the x just goes away, this is 1 over 22, plus 1 over 1.5, I'm going to bring this 1.5 out, and then I'm going to do this as, you have to be careful here, this is going to be 20 minus x squared plus 15 squared, squared, or square root to the 1/2, right? And so I take the derivative of this, it's going to be 1/2. So first I'm going to do power rule. I need to bring the 1/2 in front, leave everything else alone. Sorry, this is a squared in here. But because the inside is an x, I got to multiply by the derivative of the inside. The derivative of this one, I'm going to have to do power rule on this. It's be 2 times 20 minus x squared to the 1. And then because this derivative isn't x, I got to take the derivative of this part. It's negative 2x. And then I got to do the derivative of 15 squared, but that's just 0. And so I'm done here. So this is 1 divided by 22 plus 2 times 1.5 is 3. 1 over 3 times 2 times negative 2, so that's going to be negative 4x here, times 20 minus x squared, times all of this, which is square root of 20 minus x squared squared plus 15 squared. Actually, this squared is, oh man, I messed up. This shouldn't have been a squared in here. This should have just been x. My bad here. Making slight mistakes. Let's redo this derivative. This is 20 minus x quantity squared. That's where my square went when I re-added that in there. So times the derivative of this is 20 minus x times negative 1. Okay, so there we go. So what that does is I had an extra x in here that I didn't need. So this would have been 2 so this is 3. Yeah, it's 3 here times negative 2. So negative 2/3. 20 minus x. No square there, just 20 minus x divided by the square root of this. Okay, yeah, and then this squared doesn't exist either. Okay, and I would need to know when this is equal to 0. So, kind of annoying. We're going to take it one piece at a time. We're going to move this to the other side and then multiply by 3/2. So it's going to be 3/2 times 1 over 22. That's equal to 3 over 44. And that's just equal to all of this to the other side. Be 20 minus x over the square root of 20 minus x quantity squared plus 15 squared. And then I'm going to cross multiply, so I'm going to get 3 out of 44 times the square root of 20 minus x quantity squared plus 15 squared is equal to 20 minus x. Then I'm going to square both sides. So I'm going to get 3 squared over 44 squared times 20 minus x quantity squared plus 15 squared is equal to 20 minus x squared. So I can group the 20 minus x squareds together, right? Because let's just do 44 squared. This is 1936. This is 9 over 1936. I'm going to distribute this here. 20 minus x squared plus 15 squared times 19 over 36. 15 squared times 9 is 2025 over 1936 is equal to 20 minus x squared. I can group these together by subtracting here. So I'm going to get 2025 over 1936 is equal to 1927 over 1936, 20 minus x squared. I can multiply through to get rid of that. So 2025 divided by 1927, I get 1.051 is equal to 20 minus x squared. Take the square root of that. I get 1.025 is equal to 20 minus x. And so x will be 20 minus that. Let's be 18.98. Okay? So that means he doesn't need to go all the way 20 and then turn a right corner. He's going to go pretty close. And that has to do with the fact that his swimming speed is so much slower than his running speed. So that intuitively makes sense. The answer logically makes sense. What are the dimensions of the rectangle with the largest area that can be drawn inside the unit circle? So I'm going to draw a rectangle in here inside of a unit circle. There's a couple of ways we do this. I'm going to say this is the value xy. Okay. If I were to draw it on axes, the equation of a circle is x squared plus y squared is equal to r squared, right? If it's centered at the origin like this. And so what we would say is, well, unit circle's radius 1, so x squared plus y squared is equal to 1. And if this is xy, the coordinate xy, this is negative xy, this is negative x, negative y, etc., x, negative y, then this length is 2y and this length is 2x. So the area here is equal to 4xy, right? 2x times 2y. Okay, and so I can solve for y. Y is equal to square root of 1 minus x squared and plug that into here. So the area is equal to 4 times x times square root of 1 minus x squared. And just to write it in power form so we can do the derivative properly, or exponent form like that. And so the derivative is equal to 0. The critical numbers occurs when I take the derivative. So I leave the 4 out. I do x times the derivative of this, which is 1/2 1 minus x squared to the negative 1/2. Then by chain rule, I'm going to multiply this by negative 2x plus the derivative of x, which is 1 times 1 minus x squared to the 1/2. Here I'm going to factor out a 1 minus x squared to the negative 1/2, because negative 1/2 is the smaller exponent of a factoring. So if I pull this out, 2 times negative 2 is just going to be negative. So that's negative x squared plus, and when I pull this out from this term, all I'm left with is 1 minus x squared to the first power. So this is 4 1 minus x squared to the negative 1/2 times 1 minus 2x squared, because I got a minus x squared, another minus x squared. I want to know when that's 0. Now this part's a denominator, it's a radical. So this is only 0 when this part is 0. So 1 minus 2x squared is equal to 0. And so that happens at 1 is equal to 2x squared, or x squared is equal to 1/2, or x is equal to square root of 1/2. Technically plus or minus, but in my picture I kind of made x already positive, right? So x is equal to positive square root of 1/2. I don't know if it makes sense to you that this area would be maximum as opposed to a minimum, or neither. Because anywhere else, if I pick like here, the area would be like 0. So the smallest area is definitely 0. So the largest area is going to be 4xy. X is equal to 1/2 square root of 1/2. You'll find that if I plug it into here, square root of 1 minus 1/4. Wait. No. The 1 minus 1/2. That's square root of 1/2 also. So x and y are equal. So it actually ends up being a square. 1/2 root 1/2 times root 1/2 is 1/2 times 4 is 2. That's the largest area. All right, so now we're going to look at a couple of challenge questions. A little more difficult than the other ones. Not too difficult, but as long the key part, the challenging part is not the calculus. The challenging part is always the setup of the problem, so that you can apply your calculus tools. The calculus tools are pretty straightforward. So you're given a single piece of wire with length 10 centimeters, and you cut it into 2 pieces of wire. So I'm going to cut it somewhere here. And shaped to make like a circle and an equilateral triangle. So say we'll cut it out here in x. So this is length x. This is length 10 minus x. And we'll say I'll make a circle out of here and an equilateral triangle out of this. What are the dimensions of such a circle and triangle that maximize the total area of both the triangle and the circle? Well, the total area means sum of the area. So say I cut it into this x and 10 minus x, and then I now construct a circle out of this. Okay, and then I construct a square or a triangle out of this one. Now in this case, if this length is 10 minus x, this triangle, each side is going to be 1/3 of 10 minus x, right? And I want to create an equation for the area of this triangle using this. There's a couple of ways you can do this. We have one theorem, if you remember, if I know this is 60 degrees, I know that the area of a triangle is 1/2 the 2 sides times a sine of the angle between them. So that's one way we could do it. The other way is sort of a geometry kind of question. So I'm going to do it this way. Squared times sine of 60 degrees is 1/2. No, root 3 over 2. Okay, so that's the area of the triangle part. How about this circle? Well, this x gets stretched around to the circumference, right? So I know that 2 pi r is equal to x. And so I know the r is equal to x over 2 pi, right? And so then I know the area of this circle is pi r squared, which is pi times x over 2 pi quantity squared. And that's equal to pi x squared. Actually, the pi's will over 4 pi. X squared over 4 pi. It would be 4 pi squared, but one of them is going to cancel with that one. So the total area I'm going to get is x squared over 4 pi plus this area here, which is root 3 over 4 times 1/9. So this is 1/3 squared is 9. 9 times 4 is 36. So root 3 over 36 times 10 minus x quantity squared. And I want to know when this is maximum. So I'm going to set it equal to 0. So this is going to be 2x over 4 pi plus root 3 over 36. Derivative of this is going to be 2 times 10 minus x to the first power. That's power rule. The inside's not x, so I'm going to multiply by -1. So that's x over, like this will cancel, it'll become 2. So this is going to be x over 2 pi plus this will become 1 and 18. This is going to be minus, because this is negative root 3 over 18 times 10 minus x. And if I distribute this out, I'm going to get x over 2 pi, let's see, plus an x times root 3 over 18 minus 10 root 3 over 18 is equal to 0. So I can bring this, so first I can simplify this. So I can get x, if I factor in x, it's 1 over 2 pi plus root 3 over 18 is equal to, moving this to the other side, is 5 root 3 over 9. And so the x would then be 5 root 3 over 9 divided by 1 over 2 pi plus root 3 over 18. And I'm not really going to bother simplifying that. That might be, you can use a calculator for that. So that would be the, well, that would be x. To find the dimensions, I'm just going to use my calculator. I'm just going to round it because I don't think it's super useful to carry around like this. 5 root 3 divided by 9 divided by 1 divided by 2 pi plus square root of 3 divided by 18. This ends up being 3.77. Okay, so that means my r is going to be x over 2 pi. 3.77 divided by 2 pi. I'm going to get 0.6. So the radius is 0.6, and then the sides of the equilateral triangle is going to be 1/3 10 minus 3.77. .08. Okay, so those are the dimensions of the triangles if you were to maximize it like that. So, okay. Find the maximum size rectangle that would fit inside the ellipse with the equation x squared plus 9y squared is equal to 9. Oh, these are two different problems, so I will fix that. Yeah, find the maximum size rectangle that would fit inside it. Yeah, actually, this is a second problem. Let me just correct that real quick. Just didn't transcribe correctly. So, yeah. Okay, maximum size rectangle would fit inside this ellipse. X squared plus 9y squared equals 9. So the ellipse looks like this. You know, your sketches of an ellipse. It's longer in the, well, I would divide it by 9, so it'd be x squared over 9 plus y squared over 1 is equal to 1. This is a standard form for an ellipse. And so it's going to be longer in the horizontal direction. These are going to be the vertices 3, 0, negative 3, 0, 0, negative 1, 0, 1. And then I'm trying to find a rectangle that will fit in here. Okay, you don't actually need to know the picture of this ellipse. I kind of just useful to do it, but like basically it's going to be similar to the way we did the circle, except the equation is going to be slightly different when we solve this, right? So the area of this, if I pick an arbitrary point x, y, the area, this is going to be 2y times 2x. The area is 4xy. But this time when I solve for this, I don't use a circle equation. I say, well, y is equal to square root of 1 minus x squared over 9. So that's going to go here. So my area is going to be 4x root 1 minus x squared over 9. And so then I'm going to use this derivative instead of the circle equation. So it's very similar to the circle one, just a little bit more tricky on the slight change in the algebra. So I'm going to have a 4 here. I'm going to do, and again, I write this as 4x 1 minus x squared over 9 to the 1/2, so I can do the power rule properly. So it's going to be x times the derivative of this, 1/2, 1 minus x squared over 9 to the negative 1/2, subtracting 1. But the inside's not x, so I'm going to multiply by negative 2x over 9, right? And then plus the derivative of x, which is 1 minus x squared over 9 to the 1/2. Okay. So then I'm going to factor out a 1 minus x squared over 9 to the negative 1/2, because there's one of these in both terms, and the negative 1/2 is the easiest one to pull out. This 2 is going to cancel. This is going to be negative x squared over 9, right? Plus, pulling this out just leaves me with a 1 minus an x squared over 9. So this becomes 4 1 minus x squared over 9 to the negative 1/2 times 1 minus 2x squared over 9 is equal to 0. Now this is going to be on the denominator, so really this part just has to be 0 in order for the whole thing to be 0, right? So I'm going to have 1 minus 2x squared over 9 equal to 0. And so this would be 1 is equal to 2x squared over 9. So 9 halves is equal to x squared. So x is equal to root 9 over root 2, square root of both. That's 3 over root 2, which is 3 root 2 over 2. And then that's my x dimension, right? Well, that's my x coordinate. And my y coordinate would be square root of 1 minus x squared is 9 halves, so 9 halves over 9 is equal to the square root of 1 minus 1 half, because the 9's cancel. That's equal to square root of 1 half, which is equal to 1 over root 2, which is root 2 over 2. Okay, so that's my y coordinate, that's my x coordinate, but really the dimensions are twice as long because it's an ellipse. So my dimensions is going to be 3 root 2 by root 2. Those would be the largest size rectangle that I could fit. Find a point on the line y equals x squared. That should say x to the, let me check real quick. That is x to the x squared. X squared, that's what I thought. Y equals x squared that is closest to the point 0, 1. Okay, so y equals x squared here and here, and 0, 1 is this point here. And I want to find the point along this curve that has the shortest distance between here and here. Okay, somewhere, it's probably somewhere along here, obviously not way over here. Okay, so I have a point xy, and I want to create an equation for the distance between the 2 points. Well, the distance d is the square root of the difference in x minus 0 squared, plus the difference in y, which is y minus 1 squared. Okay. Now, I need to replace y, so this is square root of x squared plus y minus 1 squared. And I do know that y equals x squared. So this point isn't just any point, it's the point y equals x squared. So this really I can replace square root of x squared plus x squared minus 1 squared. Okay. The other trick I'm going to do is, and so now at this point I can take the derivative of this and find the minimum value, okay? Because I want to minimize that distance between those 2 points, right? So this is the equation I want to minimize. But it turns out I can minimize the square and I will get the same answer, because squaring is sort of preserves order, like it's monotonic. And so if I minimize the square, it will minimize the distance also. And so the reason I do that is to just make the derivatives easier. Okay. So I'm going to take the derivative. So I'm going to take d squared, take the derivative of this, and I'm going to get 2x plus 2 times x squared minus 1 to the first power by power rule, right? And then the inside is not x, so I'm going to multiply by the derivative of the inside, which is just 2x. So this is, I can factor out a 2x, and I get 1 plus 2x squared minus 2. That's equal to 2x times 2x squared minus 1, and that has to equal 0. So that happens at x equals 0, or x equals to, let's see, I got a square root of 1 half, right? Square root of 1 half squared be 1 half times 2, yeah, like that. Plus or minus, technically, probably symmetric there. Because if it was the same, it's an even function, right? If it's over here at 1 over a square root of 1 half, negative square root of 1 half would also have that. So now we have to decide, are these minimums or maximums? Interesting that you would have any of these. So the second derivative of the square of the distance, if I were to do the second derivative, just do a second derivative test, I would have the derivative of this, derivative of this here. Which one would I do? I'll do the derivative of this. I guess I could have just, I'll just do the derivative. No, I'll just expand this out, then take the derivative. It's going to be 4x cubed minus 2x, right, if I distribute all that. So the second derivative here is going to be 12x squared minus 2. Okay, and so at x equals 0, it's concave down. So that makes this a maximum. So this is a relative. This is a max. And at square root of 1/2, it's positive, so that makes this a minimum. It's kind of weird that it makes it a minimum. And this is a maximum, but this is a local maximum, I guess. So I want to find the one that's closest. So these are minimums, so these are the closest here. So really, at x is equal to plus or minus square root of 1/2. So the points would be square root of 1/2, 1/2, and negative square root of 1/2, 1/2. Okay, because this second derivative test was yeah. Okay.